In problem number 1, we observed in the first video a ball falling down towards the ground, and once it hits the ground, it reverses its direction and bounces back up. We can assume the ball is made out of rubber due to the bounce. Why does this happen? I've split the scenario into 2 intervals. Our first interval will focus on the ball initially as it is falling down towards the ground after it is released, and then finally when it hits the ground and reaches its maximum deformation. This is the part where the ball looks like it is being squished downwards. In the momentum chart I have drawn, we see the ball is in motion, so it has an initial momentum moving to the right. This indicates the downward direction. The ball's final momentum is 0 because at the moment the ball is done deforming, its velocity is 0. Momentum is mass times velocity, so there is no momentum because there is no velocity. The final momentum minus the initial momentum gives us a momentum vector traveling to the left. This indicates a change in momentum in this interval. In our energy model, we see that the velocity decreases until it eventually hits 0. It is an open system because once the ball comes into contact with the ground, energy is released, possibly in the forms of heat and sound. As for forces, we initially only have the force of gravity acting on the ball as it is traveling down, but when the ball hits the ground, we have the force of the ground on the ball and the force of gravity on the ball. The ball here is object A, and due to Newton's third law of motion, we expect object B, which is the ground, to exert the same force back onto the ball. Our second interval begins when the ball has reached maximum deformation after coming into contact with the ground, and then finally the moment the ball reverses direction and travels back up. In the momentum chart, the ball has an initial momentum of 0 because it does not possess a velocity the moment the ball has deformed completely. Using the force of the ground, the ball will then be put into motion and moves upwards. There exists a change of momentum in this interval. The energy model tells us that kinetic energy initially is 0 due to no velocity and increases as it moves back up. It is an open system because as the ball reverses direction and moves back up, it is now working against gravity, and this needs more work, meaning less energy is conserved. Newton's third law of motion states that the force of A is equal and opposite to the force of B in the negative direction. In interval 1, we expect object B, which is the ground, to exert the same force back onto the ball.
The second video, it shows that the ball just drops, having its final momentum be at 0. So the intervals that we use is the moment that the ball is falling as our initial, and the final is after the initial contact the ball first hits the ground. So if you show this motion in a momentum chart, your initial momentum is that the ball is still moving, and your final momentum is that the ball isn't moving anymore, so having that as 0. So that means that your delta P will counteract the initial motion of the system. So this shows that our total initial P is the same, our delta P's are the same, and our final initial will be 0. This momentum chart shows that this system is an open system. This open system can also be seen in an energy conservation model. I use the energy of KE trans because we are dealing with velocity. So the initial velocity is that x is greater than 0, and our final velocity is that our final velocity will be 0. And this shows that the system is decreasing, causing energy to leave the system. Since it is an open system, I drew it as dashes, and energy can be released either through heat or sound. So if you show this motion in a Newtonian force model, the third law is applied to this system despite having the object being stationary in the end, because due to Newton's third law, it states that there is an equal and opposite reaction to any force. So even though that it is stationary, there is a force acting on it that causes that the opposite and equal reaction. This can be seen in a force diagram. So initially, when a ball is falling, there's just a force. The only force on the ball is the force of the earth on the ball. But in the final velocity where the ball was just stationary, you still have the force of the ball, the first force of earth on the ball, but you also have the force of ground or on the ball. So these two forces are counteracting each other, causing the ball to just stay stationary, which also shows in Newton's third law, where for every force there is an opposite and equal reaction to it. And Newton's law is shown as F A on B is equal to the negative of force B on A. So this is seen as when it's in the final state, the force of the ball on the ground is equal to the negative of force of the ground on the ball.
In problem number 2, we took a look at 3 statements and decided whether they are useful to understanding what we experience in real life better. My partner and I decided that statement A, a force is used up, is not useful because it actually does not make sense. Forces are always being exerted whether objects are inanimate or not. We see in this drawing a misconception that people may think. In this drawing, an individual pushes another individual. Just because the push is over with and the pusher's hands are no longer in contact with the other person's body does not mean the force is actually used up. This means energy is just transferred. So forces are still acting and will eventually act on the individual falling. The force of gravity still exists, and when the person lands on the floor, the force of the floor will act upon them. Statement B says that one object has more force than another object. We decided that this statement is useful because we know that an object with a larger mass will exert more force on a stationary object with less mass. Newton's second law of motion always states that an object will be accelerated if there is a force acting upon it. In example 1, we see 2 carts on a track. The cart on the left has a mass sitting on top and will be pushed towards the cart with no mass and is stationary. The cart on the left has more force than the stationary cart. In example 2, a person is pushing on an empty grocery cart. The person exerts more force because they contain more mass as long as the grocery cart stays empty. This is all reflected by the equation: the sum of all forces is equal to the mass times acceleration.
So for C, it states that a force is transferred from one object to another. So this was applied to my life when I was at a grocery store, when I was returning back a grocery cart. And typically the return container thing is usually filled. So what I like to do is to use a lot of force so that my cart is pushed into the end, causing all of these carts to move. And this shows that and this shows this statement because when you have a bigger force and it is applied to a stationary object, the bigger force will transfer its energy to the stationary object, causing these objects to move forward.
This concludes our responses to the makeup quiz. Thank you.